Good morning, dear students. After considering the Newton's second law, which tells us how to quantitatively estimate a force, we have to certainly talk about one important aspect, one important force that we always come across in our mechanics. It is there, whether you notice or you don't notice, and that force is to be always to be taken into account. That is what is called weight. The weight is a force which is due to the force of attraction of the earth on the body. We often come across another word similar to this weight. Will be often likely to get confused with that. Let us make that point clear here in this module. That word is mass. If somebody asks you what is your weight, you will say 50 kg, 60 kg, you talk like that. Really speaking, we are not talking about our weight there. We are talking only about mass. When you say, my weight is 60 kg, what you mean to say is, your weight is a force equivalent to the force of attraction on 60 kg mass due to the earth. That's what it means. That means, if there is a body of mass m, this is equal to 60 kg, suppose, if you say, this body is acted upon by a force of gravity, that is what we call as weight. And this is equal to the mass of the body into the acceleration due to gravity. The acceleration due to gravity is a thing which you all know. It is nothing but the acceleration of a freely falling body. If a body is allowed to fall, you just leave it freely, it falls due to the Earth's gravitation here. The gravitational force will be there on that. So because of that, there is an acceleration produced. Because every force can generate acceleration, we have given a Newton's second law. The force by mass is acceleration. Similarly, when a body is left freely for the acceleration for the gravitational force of the earth to act on it, you will find the force acting on it as equal to Fg. And that force divided by m is what is called as acceleration due to gravity. We show it with the letter G always. This is gravitational force. That itself is what we are calling as W, the weight. Therefore, weight is the force given by the formula mass into acceleration due to gravity. Mass is different, weight is different. The value of this G decides how much is the weight. Mass is not that. Mass means the matter contained in the body. The matter contained in the body means everything that is there inside the body is mass. The material as such, the content, whatever is there in that, the electrons, the protons, the nucleus, the atom, number of atoms, molecules, whatever there in a given body, all those things put together is what is called as the mass. We call it as content of the body. That is given in terms of kilograms. How is that known? There is a body which is preserved in the units and measures laboratory there in Paris, and it is a particular piece of mass, and that is called as 1 kilogram. That is made from platinum iridium alloy and kept there in a particular cylindrical form. So anything that is equivalent to that is called 1 kilogram. So in terms of that, that means as much matter contained in that is equal to 1 kilogram, wherever it is available, in whatever form it is available. It can be a kilogram of gas, it can be a kilogram of liquid or solid, whatever the case may be. So that is what mass is. Mass has a different stand always. Mass is because of the matter inside. And this mass remains constant everywhere. There is nothing to change the mass unless mass is converted into energy. If a bomb explodes, the mass converted into energy there, say. That's different form totally. Until then, as long as the body remains as the body, the mass remains as the mass. You hit it, it will go away from there. The force acts on that, acceleration is produced, it will go in some direction or whatever the case may be. But it remains as the body. You take a cricket ball that is hit by a bat, However hard you hit it, it goes as a ball only, it remains as a ball always. At the most it may break into pieces. But all the pieces put together again is equal to the ball only. It is not different. So, such is what is called mass. Mass is a scalar quantity. It has no directional importance. But what is the nature of mass? We have told in Newton's first law. Mass is a property from which we are getting inertia. The body gets inertia because of its mass. The more the mass, the more is the inertia. Mass means the measure of inertia, we call it, therefore. The measure of inertia is mass. We put in kilograms. We always put like that, in SI units. If it is FPS, we put in pounds. We write like this, pounds like that. That is mass. Whereas weight is not that. So if mass, the measure, the more the mass, the more the inertia, and therefore more force is required to make the body change its state, like what we said in the Newton's first law. See, for example, there is a mass here. You apply a force in this direction, say, and it will generate an acceleration in this direction that is given by F by m. Suppose you apply the same force in this direction. There also it will create the same acceleration in magnitude. Direction will change, that's all. But mass has no preference about it. Whether the force acts in this way or in that way, it has nothing to do. It only interacts with the inertia of that. It will tell you how much magnitude of acceleration is going to be produced because of that, as the ratio of force to mass. So, we try to understand mass is scalar quantity, therefore it has no directional preference for anything. There is nothing like measuring mass in this direction, measuring mass in that direction. The force has direction. Force is a vector quantity. If you take weight, on the other hand, see here. Suppose the same body is subject to gravitational force. There is earth here. There is gravitational force subjected there. That means the body is attracted towards the earth with a weight. This weight is given by m into g, where g is the acceleration due to gravity. So this weight is always in the direction of g. What is the direction of g? It is always toward the earth, like that, down to the earth. So the weight is always having a direction. You cannot think of weight in this direction. Suppose there is a mass here, you can't think of weight in the direction. There is no weight here at all. There is no weight there at all. Weight is there only in this direction, towards the earth. Earth is here. So we try to understand this as a vector quantity. Weight is a vector quantity, whereas mass is a scalar quantity. That is the main difference what we have. And what about the nature of this weight? Once again we will see here. As what we said now, when weight is considered as a vector quantity and mass is a scalar quantity on one hand, and that mass has no directional preference, mass depends only on the content material in the body. Mass is constant wherever it is. Suppose you take a ball here. The mass of the body is say for example it is some 5 kg is there, say, or 3 kg. I don't know what the standards are there for the cricket ball. 3 kg is there, 2 kg, whatever the case may be. So a body of mass 3 kg is here. So if you take this mass to anywhere in space, you go take it to the moon or Jupiter, anywhere else also, the mass is only 3 kg in that. It won't change. The mass remains constant everywhere in nature. It won't change. What changes is the weight, because the weight is dependent on mass and acceleration due to gravity. While mass is not changing, the acceleration due to gravity is alone changing from place to place. When acceleration due to gravity changes from place to place, weight also will not be constant at all places. Experimentally, we can determine the value of acceleration due to gravity at various places. Simple pendulum is there, a small experiment where you can measure the value of acceleration due to gravity experimentally. And we know the value generally we take for our calculations as 9.8 meters per second square, an approved value. It does not mean it is constant everywhere. We take that value for calculations in our numerical problems. It is not constant because it has different values at different places. If you take the same simple pendulum to a different place on the hill top, and work out there, you may get a different value slightly. In fact, it is having the maximum value at the poles. On the earth, if you take, at the poles, the value of G is 9.82 meters per second square. If you take on the equator, here, because the shape of the earth is not completely like that, it is a bit bulged at the equator. At the equator, the value of G is about 9.78 meters per second square. So the range goes like that. So in between the places, it will be having some value in between these two. So the value of G depends on various factors. Accordingly, the weight also will be changing at different places. What is the factors that why is the value of G not constant at all places? There are so many reasons for that. You will be studying this in the chapter on gravitation when you come to it there. You will know the earth, first of all, I told just now given you here, is not a perfect sphere like what we think. It is something like, we call it oblate spheroid, we say. It is a spheroid. Spheroid means the sphere with unequal diameters. The maximum diameter is the equator, minimum diameter is here. And this is poles. So wherever the diameter is minimum, the force of attraction toward the center of the earth will be more, because the force of gravitation is inversely proportional to the square of the distance that we have. This is what the square of distance is. Here distance is small, so force will be more. So accordingly, G value will be more. Here at the equator is slightly more in the radius. Therefore, you will have less value there. So you have like that one reason. Similarly, the mass distribution in the earth also is not very even. We have minerals inside, we have waters like seas, we have hills there and so on. So at various depths and various heights, at various geological conditions, the value of G will be different. You can always estimate those things also, how much it will be at a very given place, depending upon the local conditions. Every aspect can be considered theoretically, and you can work out how much would be the effect of that. Ultimately, the simplest thing is find out by doing a small experiment like simple pendulum to get the value of G at the given place. The value of G at given place is best known only by experiment, not by any theoretical values. Theoretical values will tell you how the other factors are influencing it only, to the extent we can know it. Effective value is only known by experiment. So this is how it changes. So the value of the weight from place to place will be changing. Not only that, if we are there, suppose on the surface of the earth, the gravitational force, even though your mass is constant, gravitational force depends on the mass of the earth there. That mass also is important there. Suppose you take your body to moon, you are there on the moon, say. Then what happens? The weight of the body on the moon there will be different from what it is here. You will find much lighter there. It becomes much easier to walk in a way. Easy to lift your body. And at the same time difficult to press your body. Naturally you have to push your hand also, leg also more to come down. Because you are feeling very light. It is like walking inside water, where you lose some weight, you see, apparently. So it becomes difficult because of these reasons. Why it is like that? There the acceleration due to gravity of that moon there is less. The value of G is less there. So therefore W on the earth is always more than W on the moon. Weight on the moon. Similarly, you go to some other planet like Jupiter, where G is very large compared to that earth. The weight of the body will be much more there. Depending upon how much is the value of G more, accordingly weight also will be more. So we have like that various aspects of the conditions like mass, the local conditions, the location, the space and other things will give a feeling like the weight to the body. Therefore, weight is not a constant. It is a vector quantity with different magnitudes at different places, but always same direction on the earth toward the earth. Whereas mass is a scalar quantity, it is a constant at a given place, depends only on the content inside the body there. Right? That's what we see. With this background, now let us try to understand what weight means. Like for example, what is meant by the weight of 1 kg mass? 1 kg mass. What is 1 kg weight? 1 kg weight means 1 kg of mass into g. That's what it means. If you put it like this, it is 1 into 9.8. This is kilogram, that's meter per second square. So this is kg meter per second square. That means Newton. So 9.8 Newton. So 1 kg weight means it is 9.8 Newtons. So weight is always a force to be expressed in Newtons. That's why somebody says, so what is your weight? You should not say, strictly speaking, that I am 60 kg. You should say, I am 60 kg weight. I am 60 kg weight, we call it. Kg weight can be called as a unit in a way. Kg weight means, 1 kg weight means 9.8 Newtons. If you say you are 60 kg weight, it means it is equal to 60 kg into 9.8. You have to work out that. And then say so many Newtons we have. So accordingly our weight goes. So weight is always expressed in Newtons there. Suppose the body is in motion. Like what we said now. Even though the weight is not constant, it is constantly present everywhere on the surface of the earth when it is subjected. Suppose there is a limited case of a body which is moving on a surface like this. The weight of the body is there on the body. The body is not moving in the direction. Suppose it is moving this way with a velocity, or it is taking a turn like this with a velocity. In every case, wherever it is moving, that weight will always be there. That weight is responsible for the body as long as the mass is there in it. That is there. Therefore, it is coming up there. So, while considering all other forces acting on the body, you must also consider the weight of the body there. That's important to be known. I was telling the example on inclined plane. The body is kept on surface of the inclined plane like that. With an angle theta, suppose here. Here the weight acts vertically downwards. Just like this, it acts vertically downwards. The body is having a normal reaction force acting at right angles to the plane. Contact there. So, what happens to the body now? If it is a smooth plane, it will start coming down like this. Slip down like this. In this case, if the normal reaction is there, normal reaction is balancing the weight here. The body is moving with constant velocity, it may move. Here it won't move with constant velocity. It has to move with a acceleration down. Why? This force weight has two components. W cos theta, because this angle also becomes theta now. W sin theta here. The W sin theta force is responsible for the body moving down like this because that is not compensated by any other force. Whereas W cos theta is balanced by the normal reaction there. So, the body cannot move in this perpendicular direction. It moves only in this direction down. So, the effective force is in that direction. So, see, the weight is responsible for the motion of the body there, just like a body freely falling down. But if the body is not moving in the direction of the weight or inclined to the weight also, weight is still acting there. That is what I am trying to impress upon here. If a body is moving in a circular form or in a circular curve, also there is a weight. Suppose there is a stone tied to a string you are whirling in your hand. Then the weight of the body is acting vertically downwards. Suppose you are moving on a circular path which is vertically there, like in a circus globe, say. The weight is acting here vertically downwards, here also it is acting vertically downwards, here also it is acting vertically downwards, everywhere vertically downwards. It has no preference about the direction of your motion. It always has its own preference in the direction of force of gravitation. Towards the center of the earth, always it takes place. Suppose at any point acceleration due to gravity is not there, 0. Then what happens? Then weight appears to be 0 there. We take the example here. You take the example of the body on surface of the earth. the value of G is maximum surface here. If you go into the surface of the earth, the value of G goes on decreasing. At the center of the earth, G becomes equal to 0. That means in case the body is there at the center of the earth, its weight there will be equal to 0. There is only point where the weight is 0, because absolutely at that point 0 weight is there. The body is not there. The body's acceleration due to gravity is 0 there. You take another example on the contrast now. Suppose you take a satellite here going around the earth. Suppose this satellite here going around the earth. There is a person inside the satellite. What about his weight now? You must have seen in the films and also in the scientific videos. The weight will be 0 there in the satellite they show there. It is difficult to get the water drink there inside the satellite. You can't drink water there. Unless there is gravity, water will not go down like this. Understand? So, if everything is difficult there, if you just leave a glass there in satellite, it remains there only. It won't go inside. It won't come down there anywhere. Why? Because its acceleration to gravity at that point is effectively 0. It does not mean the weight is 0 there. The contrast here. Here G is definitely 0. There G is not 0. There is G there very much. Only that G is compensated by some other acceleration also simultaneously. There is G acting towards the center of the earth, and there is some centrifugal acceleration that is working there. It is compensating for that. So effectively it is acceleration toward the earth. Acceleration G here, and some other acceleration there, both are there. So G is equal to minus A there, that's all. Effectively it is 0. So you find a feeling of weightlessness there. Weightlessness is not weightless. It is a feeling of weightlessness. And that's what we mean say as apparent weight, we call it. Apparent weight there is 0. We say apparent weight is 0. Apparent weight is 0. Then we call it as weightlessness. So this is the feeling inside the satellite there. So the question of having a weight or not having a weight is only dependent on the body and the earth only. And the acceleration due to gravity on the earth will decide all this. Due to the earth will decide on this. Whereas there, something else is trying to compensate that is existing there, it's compensating that. Like for example, there is a body, just now I was giving the example, there is weight here, there is normal reaction here, both are balancing each other. So effectively the body is at rest. It does not mean weight is absent there. If you take this body in such a way where weight is not there to center of gravity of the earth, and normal reaction also is not there in that case, then the body is also at rest there. That's a different case altogether. This is a different case. Here both are there and they are balancing each other. Likewise here, acceleration to gravity is balanced there and creating a feeling of weightlessness. Here, acceleration to gravity is absent there completely. So that's what is to be understood. In other words, to put one more word for you to understand, if you put a body at the center of the earth, it will remain at rest there. Just take, suppose physically you take a body there and just leave it there. Imagine, it's difficult of course, it's not a practical proposal, but theoretically I am telling you. Suppose you take a body to the center of the earth and put it there, it will remain there constant. It won't move from there. Just leave it there. If you leave a body in the satellite, it won't stand like that. It will be going along the satellite. It won't remain there like that. If you put the body outside the satellite, put your hand outside and put there, then it will certainly fall to the ground. It won't stand there always. This is what is to be understood. Because there the balancing factor is withdrawn once you keep it out. Therefore it starts falling down. It will have weight definitely in that case. There is another small point to be referred to in this connection, maybe not very important at this stage, but just make a mention of it because you will be hearing about it later in higher physics when you go there. There is what is called as inertial mass and gravitational mass. there are two aspects of the mass to be understood here: inertial mass and gravitational mass. When you take a body, it is having weight because there is a gravitational effect on that. Gravitational force is acting on that. Such a mass is called as gravitational mass. That means if you call the weight of the body as W, it is given by mg, where m is the mass of the body. This mass is what is called as the gravitational mass because it is subjected to the gravitational force of the earth, and that is W by g. That is, when a matter contained in the body is subjected to the gravity, then we call it as gravitational mass. There may be the same body taken into space where there is no gravity at all and kept there, suppose. You keep a body in space where this gravity is zero gravity. Then what happens? That mass is not called as gravitational mass. That mass is called inertial mass now. What happens to a mass? Suppose you take a body and keep there in space. Just keep there in space. What happens? The body remains there. No force on that. No movement. At rest. Completely at rest. No force acting at all. There is nothing like net force zero. There is no force at all there in the gravity space. Therefore, it remains at rest. That mass which is subjected to now only one property in it, that is called inertia. Inertial subjection is there. That is what is called as the inertial mass there. Suppose now you want to find out how much it is. How do you find? There is no method of finding that there. Otherwise speaking, no balance can measure it. What to do? Apply a force on that. When you apply a force on that, what happens? Acceleration is generated. So you will apply a force and acceleration is generated due to a mass. And this mass is due to the inertia. Because of the inertia in the body, the force applied will generate a proportionate mass there. So the proportionate acceleration there. So we find the acceleration as this ratio. If you now calculate that mass as the ratio of the force and acceleration, then you will find it as inertial mass. This is the way of measuring inertial mass. You want to measure gravitational mass, what will you do? You don't have to go to space there. Take to a balance. In the balance you will have two pans here. You will keep some weights here, some weights here, and try to balance it. Usual method is there. And you can find out the weight. Actually, you will get some mass. So many kilograms you put, suppose here. The body is kept here. We say the body is having some 10 kilograms weight. It has come. That means its weight is equal to 10 into 9.8 newtons. Automatically we will calculate like that. Here the mass is subjected to the gravitational pull of the earth. That is also subjected. So what mass you are measuring there is gravitational mass. From that gravitational weight can be known always. Weight can be known from that. So this 10 kg, what you are getting, trying to balance here in the two pans and trying to get, is nothing but gravitational mass here. So this is the way in which you can find. You can find the weight here, and this 10 kg what you find in the balance is the mass. That mass is called a gravitational mass, whereas that is called inertial mass. Both are by value may be same ultimately, but their understanding is different, concept is different. It will have a greater importance when you go into theory of relativity in a higher physics there. We take an example now. Suppose a man is having a weight of 600 Newton on the earth, suppose. This is on the earth, weight on the earth. You take it to another planet there and measure its weight there. He finds it as 500 Newton, suppose, on some other planet. This is because the mass is not changing, but only acceleration to gravity is changing. G on the earth is 9.8 meter per second square, you know. What is G on the planet now? You can find from this equation. We can compare that like this. We can say that 600 Newton is equal to the mass of the body into 9.8. That's what it is. Similarly, 500 Newton, same mass into the acceleration due to gravity on the planet there. Now we can get from this what is the acceleration due to gravity on the planet there. You can take the ratio from this. You will find that it is 9.8. You can calculate now. So from that you will get the answer. You will get about 8.163 meters per second square. You can find like that. So this is what the acceleration to gravity calculation means. That's why it is coming difference there. We take another example. Suppose you are standing on a weighing machine and your reading is shown there as 50 kg at the equator. You are standing on a weighing machine and it shows the weight as 50 kg. That means the reading there shows as 50 kg. And suppose you take the same weighing machine to the poles. What will be the value that will show there? What the mass will be there? What will be the mass shown at the poles? Actually, it is weight reading what we say in terms of kg there. So many kg weight we call it. I will put like this. Kg weight we call it. So many kg weight here. How many kg weight? Kg weight at the poles you will get. How do you understand this? That means 50 kg into 9.78. The value of G is at the equator 9.78 meters per second square, suppose. So this is your weight in Newton at the equator. What will be this value? Maybe some 49. Work out this. This value is 489 Newton. Suppose you go to the poles now. There the value of G at the poles is 9.82 meters per second square. What will be your weight now? It will be different. So the mass is the same. Mass is not changing. 50. This is 9.82. This is 491 Newton. Suppose it shows like that. 491 Newton. You are standing on a weighing machine. This weighing machine is calibrated on the equator, at the equator. You take it there. What will show the reading there? It will show a reading equivalent to this weight. Understand? That means this 491, if you take it as weight, it will show a different mass reading with the value of the equator gravity reading there. That means this reading shown there, if you put in terms of mass there, it is 491 by 9.78 at the equator. This will be something like 50.2 kg which will come there. So if you stand at the equator, you are showing 50 kg reading. If you take it to the poles there, your reading will be different. It will be 50.2 kg it will show there. Does not mean your mass has increased. Calibration has changed depending on the value of G. That's what you must understand there. So therefore the reading on the weighing machine depends upon where you calibrate it, whereas the weight does not depend on these things. Weight depends on nothing. Weight does not depend on the velocity of the motion. Weight does not depend upon the acceleration of the motion. Weight does not depend upon the bodies here or there, whatever it is. As long as it is subjected to some acceleration to gravity, it will have its own value there, always shown up. Accordingly, you have to understand it. So that is what is to be remembered. So mass also similarly. Mass is not dependent on acceleration to gravity. It goes on remaining constant wherever it is. It won't change. Take care. Thank you.